Good morning, everyone. And let's have some lecture on data analysis and storage. Let's start with the data storage part today first. If you have any questions so far, please ask as always. Quite a lot of you have already submitted many questions, so that's very nice. Just because there may be people who are not familiar with ER diagrams, I will show you a simple example of showing the relationships here in the beginning. I think most of you already know this. But just in case, there seems to be something wrong with my workbench connection to the database, but at least I can show you the diagrams. I just found out this morning and I didn't have time to sort out the problem. Why it doesn't connect? It should be very simple. Okay, so I have this local host connection somewhere. Over here I'm using this uniform server. Then I use this workbench to make connection to this test user. Okay, I can do it again. So connect here. I have a database course going on, so there are something there. So now the database name I'm using is testdb, so I edit the schema to match the name. Oops. Then add diagram. This is the place to put the ER diagrams. Let's make a very simple database where we have father, mother, and child. And so it's easy to understand hopefully the connection. So first table name is father. It's the icon here. The first field is the primary key, and then we have this auto increment, which makes it this increase every time you add a new row in the database or table. And it has first name, last name. Just in case if there are people who haven't used these databases before. Then we can add mother. So the primary key is unique for every table. So these field names can be the same because the table name will separate those. And then we have a child table. So this is the primary key. Then again, this child has a first name and last name. Now, every child has one and only one biological father and one and only one biological mother. So the relationship is one-to-many. The child cannot exist without a father or mother. There is only one exception in known history, but let's not go there. For a child exists without a normal father. So this is so-called identifying relationship. A child cannot exist without a father. But for example, if we have a database of pet animals, then an animal can exist without an owner. Then it's non-identifying relationship. So you can change the nature of this relationship with this foreign key setting here. So this cardinality, so-called cardinality, is one-to-many. This child has one and only one father. And if this man is a father, then he has one or several children. So this vertical line is 1. If there is open ball or circle, then it's 0. You see it over here. Now, in this case, there is 0-to-many relationship. Now it's 1-to-many relationship. And this identifying relationship tells that the child cannot exist without a so-called parent table. Now, if I take off the check mark here, then you see this line becomes dashed. And now this is non-identifying relationship. So in this case, the child could exist without father, and there is only one known child like that. So maybe we put it back. And it's the same thing with a mother. So here you have the tables now, and very quick introduction to the relationships in data relational databases SQL. But I'm not going to go into detail. If you have any questions, please ask. I know this is familiar to most of you. So then you should forward engineer this locally created ER model to your database system. You can do it with a forward engineer. And this hasn't been working for me today for some reason, I don't know. It's a demo effect, and I had no idea that this kind of things can even happen. It has never happened. So this gives an error message like this for the child table. I don't think it's about the tables. It's some setting on the workbench now. It can be about the model options. So I don't know if this helps, but if my SQL version is wrong, then it can give those kind of. No, it's not that. Yes, I think it's you have to. I have to edit some statements there in here. It may some of these settings here that causes this, because I haven't run into this kind of problem before. It is quite standard. I know this ask visible statements didn't work on my SQL versions before 8. Yeah. Maybe if I remove them completely. Yes. I think that was the reason before. Let's see if it helps. Okay, there's something funny here, but if you can solve this problem, please, for example, use the Teams page if you reproduce this. But the main thing was just to demonstrate the AER diagrams. They should, in principle, they should work. Now, for this week, we have had this MongoDB, and there were problems with the links, as discussed last week, and it was quite easy to install it on Ubuntu. Instructions are quite straightforward. If you have sudo rights, then you can do it. If it doesn't work, you can ask me or Teemu. Teemu is, as you know, he is the guru of this kind of things, so he can help most likely better than me, better than I can. But at least for me, this went just like described. And then you have the command line where you can start making the assignments. Here is the tutorial, which is quite nice. I couldn't have written better myself. And here are the exercises, MongoDB workbook. So this is very good material for self-study. But let's not go. I'm not going to go through the MongoDB syntax like I didn't go through the Python coding, because that's, I think it's a waste of time, because you can study those. Some words about the machine learning notebook. So here is the link to the GitHub, where you, as I have already said, you can download all the materials. And now let's start with this first chapter. You can use this Jupyter Notebook either by online, or you can use it by installing it for your own machine. Both seem to work. Okay, let's try the web version. Now you'll see the code here and open in Colab. Okay, that's what's chapter 2. Let's go to chapter 1 first. So I like the simplicity of this. You don't have to install anything. But if you want to install, then you should install the Anaconda 3. Anaconda Navigator, which among other things includes this Jupyter Notebook. Take some time, my computer is dying. So here you can run the commands where you have this arrow, then takes a few seconds to run those. So here it uses the Python version 3 and then import this scikit-learn. Then it prepares the data for these exercises, which we go through soon. There are lots and lots of code and different commands, so it's impossible to try to sort out everything. But I guess you can learn by doing. That's how I have studied this material. And this Jupyter Notebook is great for this purpose because you can see the comments and everything. And in principle, this should work. All right, it has worked so far, but I have been very unlucky lately with my programs. Yesterday also, it was terrible. Nothing worked. Things that have been working for years just didn't work. Okay, I try to start this one. So last time we were somewhere in chapter 1, the machine learning landscape. We shall continue from this instance and model-based learning. So one way to categorize the machine learning system is by how they generalize. And the instance-based learning means that you have some example data where you draw conclusions, like the email spam system. It's easy to see such emails that contain some phrases which you can measure the similarity between different mails. So this is very basic similarity measure. And then the system would flag an email as spam if it has many words in common with non-spam email. The system learns the examples by heart and generalizes to new cases using some similarity measure. In here, for example, the new instance would be classified as triangle. because the majority of most similar instances belong to that class. And these are training instances which are already in the set, and then you add a new one and compare it to the original ones. Then the model-based learning, you have some mathematical model for which you can build predictions. And this is called model-based learning. Okay, in this example, I have no idea what kind of mathematical model will produce this dashed line. But the next example is the linear line fitting, which is very easily understood. And this is the example that is in this Jupyter Notebook. So this OECD's website, where is the so-called Better Life Index data, and then stats about the gross domestic product, or GDP, is from the IMF's data website. Then these two data sets are joined, and you are interested in these two parameters, this GDP and life satisfaction. Okay, it's easy to understand that, or at least you can make an assumption that the richer the country, the higher is the life satisfaction. And if you look at the data, you clearly see some increasing trend. So there is some level of correlation between the GDP and life satisfaction. So it is possible to model this data with a straight line that gives the best possible fit to the single data points. I think this is quite basic math. It's the Excel trend line. I have already said it. So line that half of the data points is above the line and half are below the line. You may also know that this is so simple case that you can calculate the line equation analytically from partial derivatives. But it is also possible, of course, to make an iterative algorithm that tries different slope and constant values to the dataset and finds where the error is minimum between the line and the data points. So as it is always with real world data, the data is more or less noisy, which means that there is some randomness in the values. But clearly this is a linear function. And that's we call model selection. If you have a more complicated data, it can be in several dimensions. Now we have only two, but it can be tens of thousands in some complicated cases. So here is the basic formula for linear equations. So you have, this is the y value or vertical axis value is some constant plus the slope of the line and then the x value. GDP is X, life satisfaction is Y, constant plus slope. And of course, this constant value gives you the intersection with the vertical axis. If you have the constant value is 0, then you get some red line like this. Here the constant is 4, it crosses the vertical axis here, and here is 8, and it crosses it here. And of course the slope, if it's negative, then you have a decreasing line, and the higher this value is, then the steeper it rises or descends or ascends. But now there is only one unique combination of these two parameters that fit these observed values the best. So this is a linear regression algorithm. You feed it your training examples, which are these dots here. And it finds a parameter that makes the linear model fit best to your data. And this process is the training. We train our model. In this simple case, it's quite easy. But as said, it can be very complicated. But for this course, it's most important for us to understand the different terms and the general process. I think it's impossible to go very deep into these things. Then you can use these skills in your, for example, in your projects or in your thesis. I guess there is a lot of demand for this. People who know at least something about these things. So okay, but now here is the result. So here is the result of the training. We have trained our model to fit the observed data as close as possible. So here is the constant and here is the slope. Okay, now, of course, you can make predictions for any data points in this, for this line. For example, if you want to know the life satisfaction of Cyprus's people, I don't know how it's pronounced. Cyprus is a small island in the Mediterranean Sea. So they have this GDP 22,500. So then you can predict that their life satisfaction is for about 6. So 22 is about here. And you just either plug in this value to the formula, then you can calculate, or you solve this equation for life satisfaction. Quite simple, very basic math in principle. But this, of course, can be generalized to very much more complicated situations. Okay, here is the Python script using this scikit-learn package. Here is the data loading into these variables or vectors. So you see they are, the original data is just CSV, comma separated values. So there are, the values are like the name implies, separated by commas. Very simple file format. And as you see here, this original script downloads those data sets from GitHub. And then it sets them in some file or some directory. Okay, we don't need to know about the exit path. Main thing is that it runs okay, hopefully. Now that went well. As you see here, if everything goes well, then you get this green check mark. And now the whole this Python script from this, okay, this is exactly the same as this one here, is run at once here. Okay, here is the file reading stuff. Okay, I don't know exactly what this prepare country stats does, but okay, it prepares those X and Y values from this NP dataset. And it plots the data. Then here this program chooses this linear regression model from this scikit-learn library. It's very large, and if you look at this, for example, the scikit-learn, you could use all this code just by studying this. It's so complicated. But it's not the purpose of this first introductory course. We just take those examples with gratitude and run them, and then we can change some values or use this as an example for the next similar exercise. Like here, I try to do the next exercise that you can take a look at these exercises or these codes from chapters 1 and 2, and then use the source code there for another data set. At least for me, that has always been the best way to learn new things. Just take a look at the old or some other code and then try to figure out what it does, because it's impossible to do all this stuff from the scratch. Okay, now you select the model, linear regression, then you train it. So in practice, you fit the straight line to these data points. And now you can predict the hypothesis value. This X new is the hypothesis GDP, and then you put it in this model predict method. So as you well see, this is an object-oriented language. Clearly, this model calls its classes method fit or predict. And here you see the result. The result is here, about 6. Now there is nothing very interesting. Here you can of course change the Change the model from linear regression to nearest neighbor, k nearest neighbor. Okay, let's see if it works. Okay. With this another model, model 1. Change the name, yes. It gives a slightly different result. I don't know. In fact, I don't know exactly what the k nearest neighbor regressor, how it calculates model, but I think it's some kind of, it takes some 3-point average, I would guess, according to the name of the function or method. Okay, please ask if you have anything to ask. Hopefully this is quite simple. So the main steps we have taken so far, this which can be generalized to any data. We study the data, select a model, and then we train the model on the training data. And what the learning algorithm does, it searches for the model parameters or model parameter values so that it minimizes some cost function. We get to the cost functions a bit later. Some challenges regarding these machine learning processes. You can, in principle, you can have either bad algorithm or bad data. And it turns out that the bad data is much more severe problem than bad algorithm. Maybe the most difficult or bad thing is that you have insufficient quantity of training data, so not enough data points. So in general, it takes a lot of data to train a machine learning algorithm. For example, image or speech recognition, you may need millions of examples. So here you see the result of some speech recognition. So the point is that here you have the millions of words it tries to recognize. So all the algorithms perform almost identically. So the number of data points is the critical one. The test accuracy increases much more in accordance with the number of words. The algorithms are quite the same. So all the algorithms, including fairly simple ones, performed almost identically well on a complex problem of natural language disambiguation once they were given enough data. So the data matters more than algorithms for complex problems. Another thing is that you may not have a good representative set of data. So it can skew your model. And what this means in practice. Now you see, if you add, in this example, you have added 3 more countries to this plot, which were not in the original dataset. So now the best fit line is completely different. This black versus this dotted. So it seems that the very rich countries are not happier than moderately rich countries. And some poor countries seems happier than these rich countries. So by using a non-representative training set, we trained a model that is unlikely to make accurate predictions, especially for very poor or very rich countries. So this is true for any data. So you must have enough data, and the data must be representative of this problem. If you have some data missing, then you can get completely wrong results. So it's crucial to use a training set that is representative of the cases. If the sample is too small, you have a sampling noise. So too little data points, you have very inaccurate result. But if you have very large sample, it can be flawed. It's called sampling bias. The sampling bias in this case means that if we omit these 3 values, the result is biased with these blue dots, or these red ones are what are added here. So this dotted line is biased, which is called sampling bias. Now, this book was written before the last, or the, at least, I don't remember which year, but maybe before Donald Trump's presidency, because there was a sampling bias in these pre-election polls. It was predicted that Hillary Clinton will win, but they didn't have enough votes in the polls from the Rust Belt, for example, which had very large Donald Trump population. So you also should always be very wary of that. Not Donald Trump, but this sample bias. Poor quality data. If you have some automated measuring system, for example, then it's always possible that it measures wrong values. It may have calibrated wrongly, or it can misfunction otherwise. And also, if you have yes, we hopefully come to that later in this lecture. So poor quality data. Of course, people make mistakes too. So you in machine learning project, you will spend quite a lot of time cleaning up your data. There can be values that are missing altogether, which can be then interpreted as zeros, which of course messes the model. So you must, if you, for example, the measuring device just outputs not a number or zero or empty string or something, then you must decide what to do. Do you reject all the data from that data point, or do you make some guess about what was the data before and after this zero or empty value and so on? For example, with median or average value. And it's, for example, here, if you have some completely, for example, some zero values here, then of course the fit goes wrong. And then there can be features that are not, you don't need, then you should remove those from the model. Or you can combine different features to one. Then about bad algorithms. Here is an example of overfitting. In this case, you have some very high-level polynomial which you have fitted into this dataset. So of course it goes through almost every point in the data. But it's very, as you well understand, it doesn't make any sense. This is called overfitting. So clearly the linear or line fitting gives a better estimate of life satisfaction than this high-level polynomial. So overfitting happens when the model is too complex relative to the amount and noisiness of the training data. Then you should, for example, in this case, lower the degree of the polynomial or increase the data, reduce the noise, which meaning fixing data errors, not the numbers, and remove data points that are clearly wrong. Then you can also use so-called regularization, which means that you can limit the range in which your parameters can vary. So you have some knowledge of the data that it must be in these limits. So it can't be anything. For example, here this blue line is regularized, so it can only vary in some limits. And it actually generalizes better to new examples that it did not see during the training. In practice, you have when you have the constant and the slope, you can put some limits, which are called hyperparameters. So these hyperparameters are outside the learning algorithm. As such, they are not affected by the learning algorithm itself, but they must be set prior to training, and they must remain constant during the training. So in this case, you may have some upper and lower limit for the constant value and upper and lower limit for the slope, which tells the algorithm that you can't go beyond these limits. I originally was working in atomic physics, where we studied spectral lines of photoelectrons, so electrons emitted from gas samples. And then we knew that the line width should be equal to all the spectral lines. So then we made this hyperparameter assumption that the line width of these spectral lines could only vary in a similar way. So they were some milli-electron volts wide. Then later I worked with the radiology department as a trainee medical physicist. And then we used these hyperparameters to limit the gray levels of, for example, MRI or CT images. We know that the gray levels, for example, for brain tumors should be in this range of values. It couldn't go below or above certain values and such things. But that was very long time ago. Now, next we may take some look at the testing and validation, which hopefully, at least at some way, answers Karim's question. So the only way to know how well this model we have created will generalize to new data points or new cases is actually to try out to put the model in production and monitor how well it performs. And this is, in practice, is done by splitting the dataset in two before this model training. You have a training set and the test set. So you train your model using the training set and you test it using the test set. And then you have some measure of the error rate. We get to this later in more detail, but if, for example, if you are classifying things, you can have false positive, so you classify some object correctly, or you, sorry, so you can have true positive value, so you classify the object correctly. You can have false positive when you classify it wrong, or you have true negative or false negative. So then you calculate or count how many true and false classifications you have, and then you can calculate, for example, some goodness measure. But we get to that later in more detail. So usually you use 80% of your data for training and 20% for testing, unless you have very large data sets. So evaluating is quite simple. In practice, you get some goodness value for your data, how well this test set will perform in this model that you trained with the training set. But then the situation may not always be so straightforward like here, that you instantly see that it's linear. The connection between those variables is linear. It may be very much complicated, and you don't know what it should be, or what level, or how high level polynomial you should use. Then of course you can train both models and compare the goodness value. Then you should of course choose the value of these hyperparameters. The point here is that if you measure the generalization or measure the error multiple times on the same test set, you adapt the model fit perfectly to this exactly set of data, and it still may be unfit for new data. But let's not go further. That it's not. I think that was the most important part of the that thing. I'm not going through every detail. Well, we still have some time, so maybe we start this chapter 2. Which is an example project. So it's a population of California housing prices dataset from the 1990. It's 30 years old, but it does serves its purpose. So the task is to build a model of housing prices in California. And this data includes such metrics as population, median income, and median house price for each block group in California. And block groups are the smallest geographical units for which the US Census Bureau publishes sample data. And in this we call them districts. And your model should learn from this data and be able to predict the median housing price in any district given all the other metrics. And now usually in one machine learning project is just a part of a longer pipeline. In this case, this component we are doing takes the district data and then gives estimate for the district pricing, which is further used for investment analysis. And there are other signals added, and then the bosses are making decisions about the investments. So this is called a data pipeline. So these different components of the pipeline run asynchronously, and each component pulls large amount of data, processes it, and spits out the result in another data store. And then later it will be used by some other maybe some other component of the system. So now I have been talking about the performance measures. So if you have numeric data, like the linear model we saw before, then you can use, for example, this root mean square error. So you take this y is one data point, and this hx is the function value of a function in this point x. So you calculate the difference between the function or the line, straight line, and the data point. If they match, so if the data point is on the line, then of course this will be 0 and it doesn't add any error. But the larger the difference between the function and the particular data point, you see here it's squared. So the larger the cumulative error, there is a summation. You sum over every data point. You have m data points. You sum the difference between the function and the data point, and you get one value as a result. In general, you can have more than one value that you study. In the previous chapter's line example, you have only one value of x and y. But in this now in this California dataset, you study four different data sets. So longitude, latitude, number of inhabitants, and median income. So this X is a matrix that contains all the features we are interested in. And here is the whole data set. So here is for example, here is the X1 is the first data point. In here you have all the, in this case 2000, M is 2000 data points. And each row in this matrix contains these four values. This is transposed, so this vector X is converted from the vertical to horizontal vector. This may be a bit complicated math, but really it's not that hard if you think about it. You have just the values you are interested in one row of a matrix. And then you have m rows. So the h is the prediction function. In previous chapter, it was the linear first order linear equation, constant plus slope times value x. And when, in this case, when the system is given the instance future vector x, it outputs the predicted value y. And the RMSE is the cost function, so this should be minimized. So it varies this function 8 parameters so that it minimizes this. Oops, now I pushed wrong button. Where did I go? Okay, minimizes this. Okay, this is computationally, this is quite costly because there is this squaring of the difference. Okay, nowadays the computers are so fast that it really doesn't matter in moderate data sets, but then if you have tens of millions of data points in several dimensions, then it may start to matter. So another goodness value or error value would be the absolute value, which doesn't require the squaring, which is hard computationally. But this just takes the absolute value. The error is always positive and sums the absolute values. So-called Manhattan norm, I didn't know that one. Okay, here is the instructions for the Python code and the Jupyter Notebook. Download the data. Yeah, okay, here again you see the same download route. It fetches the data, and this works also. Quite nicely, although it takes some time. But let's get the data and then continue from there next week. Okay, here it downloads the tarballs from the GitHub and extracts those. You see, Python has very nice feature. It all has this tar file extraction and unzip features built in, among many other things. So here, fetch housing data, then import pandas and define the housing data. And here it should be loading the housing data. Now you see it here. Housing head. The housing object sends a call to its class's method head, which gives the first 5 lines. So you see some feel about what there is in this data set. So longitude, latitude, housing, median age, total rooms, total bedrooms, population, households, median income, median house value, house proximity. And then housing info gives you the data types of the parameters we are dealing with. The value counts method gives the count of different classified values. For example, in ocean proximity, you have strings inland near ocean nearby island. And this housing describe gives you the basic statistics. So this is quite, from at least I think this is quite easy to understand what there happens. And Matplotlib is plotting tool where it takes some time, but here you see histograms of different variables. Now I don't exactly understand the axis scales. Okay, longitude, latitude, those are median age, housing median age, I guess it's people living there. How many for every year there is bar that tells, for example, here that 20-year-olds are a bit over 400. Okay, maybe it's explained here better. I don't remember every detail. Haven't done my homework that easily, that well. Okay, I think it's the housing median age. It's the age of the house. But okay, maybe we stop here. I have to study in detail this in more detail, so I can explain it better. What we see here and what we should do. But we continue from here next week. It's nice to see that there are at least some people present, some participants here. But let's continue from here next week. If you have any questions now, please ask. But we have this support hour on Thursday. Otherwise, I will stop now this recording and have a nice day. See you on Thursday next week.